be Bettina for a day and help us with recording and note taking and everything. Thank you so much. Today we have a great speaker, William Bill Miller, who is the Senior Director for Research Computing and Data Scientific Computing and Imaging Institute and Center for High Performance Computing at the University of Utah. If you had a chance to look through the flyer, Bill has impressive resume and does really interesting things, AI related, um, especially related to scientific computing and imaging, and applying computing research with real-world impact. Um, this institute was founded in 1994, and I'm hoping that it's thriving since then, contributing to researches in biomedicine, energy, geosciences, defense, etc., etc. Today's topic on presentation will be AI infrastructure for discovery and innovation, what's new and where we're going. And if we let Bill start his presentation, let's listen and Q&A. Bill, how do you prefer? Should we interrupt you and ask questions or wait to the end? Or maybe you break whenever you feel is the right time to take questions, and we'll do it whichever way you feel is more appropriate.
I'm happy to be interrupted if people want to. I just don't know if I'll see the hands up. But let me first start with the slides. People see that?
We can see it, yes.
That looks okay. Okay, and now I'm seeing what I can see. Great. Okay. So sure, people are free to pop in with questions, or I don't have a million slides, so hopefully we'll have time for a Q&A at the end too. I as you said, Mitya, I don't know the audience, so I've tried to calibrate. When I was in graduate school, I guess one of the first little group meetings where we were looking at some published paper, the professor said, well, just because everybody you think knows about this research doesn't mean they actually do. So start with first principles and in any meeting that you have. So I've tried to start with that. A little bit about me, as you heard. So I've been at the University of Utah since September, so I'm still pretty new. I spent a good 6 months of my 8 months here peeling the onion and making sure that I knew what we had, the assets and all of the different things at the campus, including at the Scientific Computation and Imaging Institute, SCI, and at CHPC. And then at the same time, we were doing some very big projects that CHPC had to deliver for the campus. One is the AI supercomputer I'm going to talk about today, and another is a regulated research environment for sensitive data research with computation that we're also building separately, which I really won't talk about today. But it's been a great ride, and I've also been learning a lot about Utah writ large through a lot of the activities I do. So I'm very glad to be here. So let me launch in. I'm going to cover just a little high-level backgrounder because, again, don't know what I know. There's interest in AI here, obviously, but I don't know what people know. So I'm just going to start with a little bit of background and then go into what's new and where we're going. So I thought I'd step way back, way back, just to start 400 years ago, let's say, with Galileo. And what you see in the middle is his telescope, one of them. And on the left is his last major book about the basically comparing the two known systems or theoretical systems about how the world is constructed, how the universe is constructed. One is the Earth-centered one, which was the preferred model for political and religious organizations and the world. And then there was the Copernican model, and then also others who were showing that there was evidence that, well, actually the Earth wasn't in the middle and maybe the sun was in the middle. So he was able to take this instrument that he discovered. Well, he read about from the Netherlands that was actually not used for as his telescope, was used for making images locally bigger, like a microscope. Turned it around the other way, tweaked it a little bit, and was able to make the hand-drawn image on the right, which was the basically the solar storms and sunspots on the sun. But the important thing was not that there were sunspots and people had seen them before, but that they were moving. And that meant that the sun was not perfect. It was not ideal in the ancient Greek way that many people were trained into. That the heavens were perfect, and there was a lot of imperfections in the earth, but everything beyond the moon was perfect, and that wasn't true. And he also showed that there were moons around Jupiter, so not only the Earth had a moon, and this all got written up, including in this book. The book didn't go too well for him. It was the last book because then he got excommunicated for this and didn't have a happy life after that. But it was a seminal piece of work. But the thing that's sort of a digression, but the thing I wanted to point out here is that, we know a lot about a telescope now. It's 400 years worth of experience. This is a deterministic input-output thing. Light comes in, doesn't matter what kind of light comes in, it does the same transformation and you get an image out. Doesn't matter what data you put in there, what comes out is the same. I mean, it's a different image because the data is different, but the transformation is similar. Not only that, but we know all about, the deterministic way of building these things, not only for optical telescopes, but for radio telescopes and all sorts of other sensors, to the point where now we can do things like this. This is a picture of the black hole in the center of our universe. It was put together, first published in 2018 after years worth of work, and it's not based on one telescope, it's based on all the other telescopes on the right there. These are radio telescopes across the world, bring all the data into one place, do some magic with math, and you produce this image. It was a very, very heavy lift. There are newer images as well after this one. But the point is that we know all about the instrument, how to build them, and we know about the math, and we know that what goes in is going to come out, so we can predict what we're going to see. You can even simulate that in a computer, and then you get the real image. So compare that with neural networks and in our AI world. Okay, basically AI is in our current era is based on neural network, artificial neural networks, which is based on how the brain it works with neurons. And the brain is a very complicated device that is very kind of messy because it came out of evolution. But the essence has been very useful is to abstract that out and say, look at these connections between neurons. You add, the signal comes in, you add things and you get an output, you take that output, put it in another one, and you can actually make this thing learn things. In fact, it's one of the seminal papers on the right there, ImageNet. People first really took a lot of images and then tried to train a neural network to produce a model, which was using a new algorithm called deep learning that was the early stages of that allowed us to now do the AI at scale that we're doing. This wasn't the paper only about deep learning, but it was about the application of that. So, but the point here is, one of the issues is, as you know, with your own brain, you take new data in and you learn stuff, and then what you do with that data will change based on what you've learned. So the transformation is not deterministic, it's indeterministic. Like, it's dependent on whatever data you put in there. If you put in certain data, you'll get a certain kind of output. And if you put in other kinds of data based on what the data that the system's already seen, it'll change the way it produces output. So that's a little more complicated. And we're really just at the infancy, if you will, of this era of AI and figuring out how to design systems to do things. Already we're seeing, really, really interesting outcomes. But again, we're just at the beginning of this science. In the last, neural networks been around since the 50s. but the deep learning algorithm not as long, and certainly the at-scale computing that we can do to put those two things together to make huge large language models, for example, is really recent. So I should also, as first principle, say, well, what is AI infrastructure? Because it's in my talk title, and people were asking me to speak on it. And just from a technical lens here, I'm going to just say, well, it's like high performance computing, and it's like big computing and big data that have been there before, but there's some special aspects to it. First, we spent a lot of time, and we still spend a lot of time with our laptops with CPUs as classic processors, but increasingly GPUs are the thing that have really driven the scale of AI much bigger because they're very fast to do simple operations. And simple operations is what you have with neural networks. It's just adding things together and getting an output. The connections between those things are also important, I'll talk about in a moment. But the essence is that GPUs have really enabled this scale and speed for AI the same way that on your phone you're using a GPU, because you can have a touchscreen and it does things immediately. That's driven by the fact that we have GPUs. Then there's the supercomputing aspects of this. And what is the difference between a regular computer like on your laptop and a supercomputer? Well, a supercomputer has obviously many more processors, but it also has these interconnections between the processors so that the processors can talk to each other and you can do things in parallel. And that makes the system even faster if you can design your software to take advantage of that. So those things are the compute side. Then, of course, on the data side, we know that AI is very data hungry, and I've shown that there's this input output, and data is really important for training. So the sources of data are important. The storage is also important because you're dealing with very large amounts of data. And then there's a caching, which is the storage that's right next to the processors, and that has to be fairly big to do a lot of this kind of work. And finally, there's the network of getting the data in and out and away and to the system. The real meat of AI is in the training and in the inference. And those are the software tools that people are using to do the learning that turn something into an AI system effectively, because you take the data, you train it, and then you ask questions about it. So I'll show that in a moment. Large language models are those same things. It has a language component to it, so you can interact with it much more facilely. And then there's analytics capabilities and workflow tools, usual kinds of things you have to do. Finally, there's the people. And I hesitate a little bit to call people infrastructure. Some people do that. And we often, when we try to say, well, we need the computing and data and software, we also have to have positions for people, because those people have very specialized skills. So you could call them, human resources or workforce, but it's just critical to everything there. Well, not only for industry dynamics of how you can hire people or not to do this work, but just the specialized skills at all these different levels you need to do this work. It makes them really part of the whole system. Okay. So what can you do with AI infrastructure? Well, as I said, classic thing that people talk about is training a model and then performing inference. The training a model is the act of feeding a deep learning algorithm with lots of data. And what I'm showing you here is a recent example. It's a foundation model created from images of the sun, heliophysics model, we say. It's the Solar Dynamic Observatory images. It was NASA that supported this. The actual training was done on an NVIDIA DGX cloud system donated by NVIDIA to the National AI Resource pilot project and it's the National Science Foundation has funded that. I orchestrated the pilot while I was there until August when I retired and came to Utah. And this is the first time that a model of the entire sun using active dynamic images and different filter channels was created. And then once you create that, then you want to ask questions of the model, which is the inference part. And here I've shown that the asking questions is done mathematically, because people are interested in specific mathematical models and specific scientific questions around this, but it's equivalent to the large language models instead of a large image model that we're all getting used to with ChatGPT and all those, where you ask it actual verbal questions and it gives you verbal answers because that's how it was developed. So those are the two main things. What that looks like more generally is that, again, we have the compute, you train the model, you do the inference, and then before that, you have to actually prepare your data. That turns out to be a very heavy lift in a lot of science and a lot of applications, because the data is not automatically usually designed to be run on a model. It's getting better now that people know that they're going to do an AI model. But traditionally, the data wasn't collected that way, especially if it was collected way in the past, or if it's, I don't know, social science research data that is kind of messy. You have to get it into a good format that then you can feed to the model to train it. And then you'll get your inference and you get your results. There's also another flavor of this that has a lot of the same things in the middle, but it's actually more dynamic, it's more live, if you will. You might have some sensors. Let's say you have some cameras that are out in Utah, which we have these projects where there are cameras in the forests, and we're looking at wanting to detect if there's fire. So, or if somebody is studying ecology and they want to use the same cameras to see which birds are flying across. Used to be that you had to take those sensors, take all of the image data all the way back to some home place where you're going to process through the images, try to figure them out. But what if you had AI at the edge? What if you had an AI model that could recognize certain features that you were looking for right there and just send those back? Well, that's a lot of compression. Now you don't have to send the whole image. You just send the name of the bird, let's say, or you can send the number that was on your database that says number one is, a red-tailed hawk. So that's AI at the edge is also a very up and coming model for how you can use AI. Of course, the model development and inference have to still be there. So with that backgrounder, I want to now jump into a little bit of what's actually new. I'm talking specifically about specific infrastructure. This is just an old physics joke. I wrote what's new in my title, and then I realized that's c over lambda, which is new as frequency and speed of light divided by lambda, and anybody can calculate this, but I guess I was punchy when I was developing these slides. But what's new here? So let me step back and talk about where I live. I have an appointment at the Scientific Computing and Imaging Institute, as Mitya said, has been around for a very long time. The University of Utah has a very long reputation, deep reputation in visualization, but also in computational research. And you can see the numbers here. We have a lot of faculty. Many of them have joint appointments with other departments across the campus, everywhere from biomedicine to ecology and to artificial intelligence and computational science, computer science. And as part of that, as you can see, there's the Center for High Performance Computing. So I have an appointment there. I have a role at the university and extending to the state activities in research, computing, and data. And I also oversee the Center for High Performance Computing, which is putting a little plug. This is our flagship, which has also been around for many decades. Actually, as many people may know, Utah was one of the first 4 ARPANET sites, so the very beginning of the internet in the country. And so there's a huge history here around computation and data and software. So we have a lot of capabilities at the Center for High Performance Computing. We serve the campus, but we also increasingly serve other institutions throughout Utah, and we're connected with the national fabric of high performance computing. We have open and regulated environments and many different kinds of systems. We're approaching 60 petabytes of data storage, and it's growing actually quite rapidly. we have a lot of expertise in facilitation, and we have this connectivity that you really have to bring data in and do computing and then send it out. So that the connectivity piece is unsung often, but that's very important. In addition to that, and working with SKI, the integration between CHPC and SKI is through the innovation piece. So there's a lot of research at SKI. There are piloting and new developments, and then that can be turned into production that we run at CHPC. So another big piece, in addition to sort of the physical infrastructure, if you will, and the research institution, there's a very big activity called the Responsible AI Initiative that President Taylor Randall started. It's a $100 million initiative, and $15 million of that is devoted specifically to infrastructure, and that in GPU computing. And we're running right now with the first tranche of that 15 million. We have high-end NVIDIA H200 GPUs running at CHPC, and also SKI has those in their own enclave. So we're able to actually work across both environments to offer those services out. And we plan to increase that capability as we go over time. But the real big item is, let me just get some water here. The real big item that that has been making the news is the AI supercomputer, which is just about to be deployed in the next couple of months. And I'm going to talk a little bit more about that right now. So we, in this current legislative session, the legislature provided 15 million for the initial operations and deployment of this system. Now, interestingly, at Utah, there's such a good relationship between the university and the state that the university felt it could commit to signing the contract to start building this ahead of this legislative session, which is interesting politics here that I'm learning about, and that is pretty amazing kind of a situation, because we started with the Hewlett-Packard Enterprise to engage for their building of the system back in, let's see, December or January timeframe. So President Randall sort of captured this in his one statement that said, "Our goal is ensuring the state is awash in computing power by building a robust and scalable AI ecosystem that benefits higher education, powers research, ignites entrepreneurial spirit." So this one quote sort of captures the broad goal. Number one, this is not a University of Utah alone system. And the legislature has also made that quite clear. This is for the state. So we are managing this for the state and to really advance our AI capabilities across the state to drive both economic and workforce development and research.
Hey, Bill, one question for you.
Yeah.
With regards to the supercomputer, have you heard anything about the state also implementing a quantum computer?
There is a lot of discussion right now about quantum, a huge amount of discussion. I have not in a position to say whether that has congealed into a project at this point, okay, but there is a huge amount of discussion about that. Okay. And also, by the way, the connection between AI and quantum is increasingly getting noted and important, and there's a lot of research and development around those two pieces.
Thank you.
Great question, though. I'd be curious to know myself, but I haven't. That hasn't come to me. I've been involved in a lot of conversations about organizing around quantum, and a lot of the agencies care about that. So here's some details about this supercomputer. It's a $50 million investment. This is a partnered public-private partnership between the state, the university, the Huntsman Family Foundation, and Hewlett-Packard and NVIDIA. Now, normally you would consider them vendors, but the partnership aspect of this is they're doing a lot of in-kind work with us, not only to help us make sure that this system works for research computing and data, but also a lot of the enablement around that training and bringing a lot of their expertise to bear over and above what the contracts are. So that's a very important thing, and it's really the first time that the university that HP has partnered with a university like this on a system of this scale. So it's designed to advance Utah as a national AI research leader. It's a state-of-the-art resource, which I'll show you some details in a second. Again, across the state, there's a whole aspect of training and workforce development to this. It's deployed already at a commercial data center that's south of Salt Lake here. And CHPC will be managing the operations and user access for that on behalf of everyone. So here's, for the people that like the details, here they are. But since I taught you at the beginning, anybody who didn't know, you'll see in these details all the different pieces. So at the very top, you see there's GPUs. So that's really obviously very important for the AI system. There's this Intel Xeon platform, Platinum CPUs. So that's for inference is important for CPUs, while training the model is GPU heavy. And then again, you have these GPU to GPU connectivity that interconnects and makes this a supercomputer, on top of also a very high-speed network linked back to the university and also links through UETN to other parts of the state. So the connectivity piece is really important here as well. And so just in May 1, the physical system has been installed at this data center. We got a first visit there. What's very important, if you don't know anything about supercomputers, the one important thing is if the lights are blinking, that's good. It's necessary but not sufficient, but they're blinking. And we were very happy to see that. They're all blinking. HPE, we're just going through their acceptance verification. We're going to send back information saying, yes, we accept the physical build. Now, on top of that, now they have to install their software and all the software stack and all the other services. But right now, the physical build is done. And you see over the right, that's Brian Haymore. He's our HPC lead. And he's just holding court, explaining to people exactly what they're looking at, which is great. So that's physically there, and we're now getting to the next phase of the deployment with the software. So just a quick timeline. We expect somewhere in early July to actually have the keys to the system, but we're not going to just throw lots of people on there immediately. We're going to do, even with a big telescope, you have to do this. There's a tuning phase, there's a learning phase, initial onboarding, and we're starting our outreach already, actually, and getting that process going. There's a lot of governance that has to be stood up. And then, we'll ease into full operations and allocation-based operations, which means people come in and make a request, and we get them onto the system into the fall and winter. It just takes a while to ramp up. Now, everybody's anxious to get things onto the machine, and we will be running it, but there's a lot of learning that still has to go on. But there's also the broader aspects. Because we're serving, the system is there to serve a broad range of institutions across the USHA institutions, and we'll be having other segments rolled out over time. There's a lot of different levels of governance and sort of the people aspect of it that it has to be orchestrated around this to make it work. And we're all working together very hard to do that. And I'm happy to answer questions about that. But the basic point is you have to make sure that everybody comes at it at the level that they can. Not all institutions, not all users are going to need a system that's at this scale or are ready for it. So you have to make sure that they're ready for it. You also have to provide the support services for people to make use of the system. And you have to ensure that everybody at the higher levels that they know that things are working well. So those are the kinds of things, besides the technical, that take a lot of attention. And in fact, we have this, what I'm calling the enablement program, which is coordinated, and we're just standing that up now to assure broad access, to facilitate readiness and support, and leverage and uplift institutional expertise across the state with this system. And of course, the governance, again, to address gaps and make sure things are going right. There's the access process that will be tailored to the different experience spaces. There's user segments that, as I say, the USHA institutions are our primary first target here, but there are additional segments. For example, K-12, we're starting conversations with the state about that, state government and business access to these systems. Each one of them has a slightly different reality to them, so we have to step carefully. And then the whole uplift and upskilling piece of this is quite important because, as I said, not everyone's ready to use a supercomputer. Some people may be ready to use smaller scale systems that CHPC offers and then can scale up to that. And that means that there's a need for a lot of training to meet the users where they are. And finally, even back at the individual institutions, there could be local ambassadors and liaisons that help diffuse expertise and bring the expertise in, including expertise that's already at the institutions that we may not know about, but can be leveraged for this if they're willing to contribute. So there's the user-facing aspect of that, there's the technology professionals aspect of that, and then there's the research and developers of AI aspects of that are all kind of in the mix. So with that, I'm just going to finish with a couple of slides on where we're going. I used this slide from my original career was in the space area, and I've discovered since I've been at Utah that Utah has a lot to offer with space. Northrop Grumman is a huge presence here, including them and a number of other industries. In fact, this is the launch of the test flight for Artemis 2 back in April, and the 2 booster rockets were built here at Northrop. And I then read that Union Pacific, which I didn't know was headquartered here, enabled the motors to be delivered to NASA. But we're going up. I think that the goal here for everyone is to try to leverage this capability to advance the position of Utah as a state, as a whole, both in the research space and innovation space, and in the business and economics and workforce. A couple of the drivers are that the agencies themselves, the funding agencies, and the milieu that I work in, that's a lot of our target because we want to be aligned with and ready for current opportunities that come along, and there are many of them in the AI space. In fact, it's being driven very heavily in that direction. So this is a slide of the National AI Research Resource Pilot. It was something that I was deeply involved in at NSF before I left, and it's 26 non-government partners, about 14 agencies contributing in-kind resources so that you can get on for free and have access to those capabilities. I mentioned that the heliophysics model was trained through this process, but NSF has subsequently put out many other solicitations for grants that are in and around focusing on building up AI capabilities across the country, even at the state level now, which was kind of new for NSF. Not to be left out and wanting to drive the bus themselves is the Department of Energy. They came out not too long ago with the Genesis mission, which is eating up a lot of the oxygen in the world that I live in, including with solicitations for teams to work on specific projects and topics across the country. So there was a lot of scramble to leverage not only our current capabilities, but advertise the new ones in grant proposals that we put out. So these are 2 major activities, 2 major agencies that are heavily focused on funding. There's many others, but I'm focusing on those just as examples. Right here at home, as you probably know very well, the governor has initiated the Pro-Human AI initiative, and that is really about trying to make sure that the human is in the middle of all of this and advance the state and the people of Utah through AI. And there's a number of pieces of this. I'm hearing more and more about this as we get into the enablement program for the AI supercomputer. It's starting to touch some of the things like, for example, that Nucleus is doing and some of the other groups. And so we're having more and more connections there, which is great. So my last slide, I just wanted to finish with final thoughts on where we may be going. In the space that I live in, we think about these very, very large systems like the one that we're deploying, like the hyperscalers that provide a lot of resources. So these are very big monolithic kinds of approaches to AI, but increasingly there's also federated AI There's AI that's appearing on your phone that's locally installed. And I think that we're probably heading to a place where there's going to be a mix, a much more mix, and maybe even a migration to these more distributed systems that can be more easily stood up and installed at different scales. I think we'll still need, if you need to train a big foundation model, you need a big system. But there are new techniques that are coming along that are allowing that to happen even at smaller scales. And sometimes smaller models that are trained well can perform pretty well compared to the bigger models. So there's a lot of research going on around that. On the use, we're talking about AI right now because it's really new. I think over time, it's going to be AI with small AI everywhere. And we'll probably talk a lot less about the fact that there is AI and about how you can do things fast. And AI will kind of, as a term, might fade to the background a little bit. They don't pay me to predict things, but I'm just thinking that this is seeing what's happening. This is what I think is going to happen for us. What that means is that it'll always be incorporated into what we're doing and in the design of infrastructure. And in fact, the infrastructure control itself will be more and more enabled by AI, and we're already starting to see that even at CHPC. Finally, I think we're all seeing this tension between the real advantages of having AI being able to create new things. Some people create images on the fly for things that have a lot of meaning and are very helpful. We can see AI, communications and large language models, people engaging with them in a very interactive way, which will only get better and better. At the same time, I think part of the learning curve here for us is the same as every learning curve with new technology, is that we have to develop a new sense of when we want the absolute ground truth about things and we want to be trustworthy versus things like creativity, and then the corollary of that is the fakery. That's still in its infancy. It's really affecting us in the secure space. For example, within 3 weeks, I'm not kidding you, 3 weeks, in the last 3 weeks, we've had 3 vulnerabilities in Linux servers announced that our folks have to go and then make sure to patch so we're secure. That's because AI and AI models are finding these vulnerabilities that have been around forever, nobody knew, and they're finding them at a high rate. So there's going to be a process of trying to, harden our systems as these new vulnerabilities are found. But that's one aspect of it. I think just in more the positive aspect is that we're learning a lot about systems. We're learning a lot about what systems can do and what they can learn, and how we can use the system. So I think we're still in that growth phase in terms of the utilization and the learning about how to use AI. So with that, that's my last slide, and I'm happy to take any questions.
Bill, regarding the supercomputer, do you know how many other states have supercomputers that are participating, I guess, federally in this program?
So that's a great question, and I will say that in the biggest landscape where there's the federal agencies that are doing things, but there's also the individual state level, which a few years ago, none of the federal agencies even thought about that. I know from NSF, we have been there for 17 years, and we didn't think too much about the state level activity. But now the states themselves, because of all of the disruption from AI, but also the focus from the federal agencies and really the opportunity that people see for advancing the position of their state. States like New York, the Empire AI, they've come out with a whole program, just like Utah has. State of Florida has gathered around because they got a big investment from one of the co-founders of NVIDIA, University of Florida, to put up a system. I think Utah is easily could say that it's still quite in the forefront of this, what we call the sovereign AI capability, where we not just working with the cloud, but we have our own system and it's at scale, and then we're building a statewide kind of capability around that. New York's doing a really great job, and I think a number of other states are. I get calls a lot about our relationship with HPE and NVIDIA on this system from other counterparts across different states, because HPE is going around to the states and saying, hey, we did this for Utah. And so there are a lot of still the state legislatures around are talking about this. So there's a competitive aspect to this. I think there's also a collaborative aspect that's emerging, and I'm trying to emphasize that in my area is that um, you know, if we're replicating the wheel, if we're doing things over and over again, let's coordinate. Let's figure out how we can make this work for everybody and not reinvent the wheel a million times. There's 50 states, right? And on top of that, the more we row in the same direction, the more agencies here and the federal government hears with a similar voice, and that allows the influence to be greater. This is what we really need. We don't need that. We need this. And so it's not a specific answer to your question about one system or another, but the broader landscape is really emerging at the state level.
So
Thank you.
what is the coordination? How do you coordinate with other states? You mentioned that, we don't wanna reinvent the wheel.
I can't speak for the governor. The governor's a really, I don't know if you've ever seen him speak, but he's a really interactive guy. And I know he's talked, for example, I went to, a couple of weeks ago, he had an innovation summit, I think down at, it was at the Olympic Center. And he talked about conversations he's having with the governor of California. Now they're at the opposite sides of the polls, right? But they were talking about how we could work together on certain issues. For example, environmental issues, water is a really important thing. So I imagine at that level, there is some coordination and competition and coordination. On my level, I have colleagues and counterparts who are doing the same kind of work across all the different institutions around the country. And it's much easier to interact. And we are constantly sharing information about, I just had a call from Brown University yesterday. They're standing up a system, wasn't specifically about AI, but we got our staff and their staffs together and they started talking about their solutions. That's very normal. I was in Boise a few days ago for the regional, it's called the Rocky Mountain Advanced Computing Consortium. It's a regional consortium where people talk. So at the technical levels, people do this a lot. And then, I have a lot of contacts at the different agencies. I did a lot of interagency work when I was at NSF, and those people are easy to engage with. It's formally though, I don't know that we've gotten to like maybe the Governors Association could stand up something on AI. I haven't followed it myself, but that would be a good place to go.
And then probably one other question I have, as a research institution, all those findings, from the work you do, how does that information reach the businesses, the public, so companies that try to get engaged with AI uh, don't perform redundant work, but can learn from findings that you have.
That's a great question. And there are multiple levels that have always existed. One is through publications, obviously. People learn things and then contact the researchers directly. Another is through partnering directly. There's more and more of that going on. For example, partnering on developing new technology, uh, engaging researchers on a topic and then working together. There's intellectual property things that always get worked out in those cases, but that's really big in AI. Not only because it's moving fast, so things are changing so quickly, but most of the researchers in AI are at companies at this point. The hyperscalers have hired lots and lots and lots of people. And so those people know how to fastly communicate with their ex-colleagues and other colleagues at the universities. And there's a lot of exchange at that level. At the more small business side, I think one of the issues is like, I know I need a thing, but I don't know exactly what I need. And that's where the enablement can come in. We're hoping to activate that through this AI supercomputer process. That part of that will be outreach and getting people together around that. We haven't gotten to that piece yet, but that's a very important piece.
William, is there any kind of opportunity for arbitrage on the horizon where, we have our data center stood up for our local projects, but we might need more compute someday for some of our projects than we have? And do we borrow compute from other states and vice versa?
I think that's a really interesting question. Actually, I care about this a lot. I'll reframe it slightly from where I sit. So I showed you mission Genesis mission from the Department of Energy. That slide, right? So they had a webinar about the funding opportunities. Now, the Department of Energy runs exascale supercomputing systems. I mean, bigger than anything else that anybody in the country has, and for research purposes and for their mission needs. And they're building more. They're building like 9 more systems that are AI based in partnership with companies. So they had one of their last slides in the webinar when they were telling people about this funding opportunity was, oh, and by the way, we expect our computing systems to be oversubscribed. So, find your own computing for the projects that you like. It's an exascale computing. How could you be oversubscribed already? But what that meant was that, and I know these folks at DOE, I spent 15 months over there when I was at NSF and led some things. And they don't have the bandwidth or the time, they don't have the people to deal with all the universities and all these different projects that they're wanting to fund. And so a number of us are getting together to say, well, we could be like auxiliary to you. We're going to run some of these projects that are part of Mission Genesis that you fund on our systems, and we'll align with what you're doing so that we can be seamless. And that way, sort of the auxiliary piece of what you have grows and grows. NSF is kind of interested in the same thing. So the idea is to have this sort of national fabric of computing capabilities. NSF already funds something like that. It's called Access. But those are just the NSF large-scale funded machines, not the middle scale that I would call us, in the middle scale of that. So that would involve collaborating with other states and other states' institutions' capabilities to use similar protocols to engage with the agency, right? So that's in my mind, that would be the fabric that would allow us to do things like what you're saying. It's like we can be seamless across, we have some space armor machine, you need to run something. We have this interface and, systems engineering that's, pretty seamless. That happens already. That is possible to do already in the various fabrics that exist. But the state institutions typically don't work that way generally, but there's no reason that it couldn't. So that's an answer to your question, which is, yeah, I'd really like to see that. And I spend a lot of time on the phone talking that exact model because I think that's going to empower everybody across the United States. There are things like the Open Science Grid that do this already. NSF funded and the Department of Energy actually funded. The Large Hadron Collider makes a lot of use of Open Science Grid. It's called grid computing, where you have basically the computing is done on pieces of computers around the country, and then there's the software that sort of connects that, but it's usually at the smaller scales. And what I think we would be talking about is like much bigger ability to connect. And I think that's going to be possible. I think I may have burned a lot of people out on this one, so I'm happy to take any questions or release you to your weekend anytime you want.
I have one question for you, Dr. Bill. So, in your opinion, like, what do you see will be the biggest bottleneck for infrastructure in AI in the next 3 to 5 years? The computing, is there lack of skill? What do you think?
Yes and yes. Yes. So yes on the computing, and I'll tell you why. We are so, I mean, I'm not kidding this. I would talk to HPE all the time, and I was like, we're so lucky that we got the project started when we did. If it would have been 2 months later, the factory at HPE, they were starting to make noises back in December. I'm not sure when we were gonna get the parts. The factory wouldn't have had the ability. And now I think markets tend to equalize, but what's going on today, right now, across the entire technology space is the lack of memory. And the memory is in server boards, and it's also in hard drives. So and that's because all of the hyperscalers are building like crazy, right? And they're making deals that tie up a lot of that. So even when in CHPC, when we just made a purchase to just get from Dell some more capabilities for our on-premises systems, boy, when the prices went up to 2 to 3x. And the time to get this stuff was like, instead of a few weeks, it was going to be 9 months. So we were lucky we even got that order in. Across the world, this is like, when it's going to happen to your laptop, it's the same story. It's the same capabilities. So that is a huge bottleneck. And if hyperscaling keeps going like this, or the amount of AI, and AI is driving some of it, a lot of data is driving the other, then, and the suppliers are what they are, there's just a handful of them, that's got to figure itself out. And I expect national scale conversations about this, like at White House levels, because we're getting to a difficult point. That said, everybody who's in business who's on this call knows that markets figure it out. So and new technologies come along that may change that. The workforce piece, that's very hard. And that's why, a lot of what I talked about had to do with, learning, training, addressing the upskilling. There's two pieces to that. One is the technology is changing so quickly. Even researchers, they hear something on the internet, want to try something, but it's like new. Like, who knows? Who knows who's the expert for that stuff? Every week something comes out that really changes somebody's picture about what they could do with AI. The other piece is that, I mean, a lot of the big companies hire the kinds of people that we want to have at the university level, and they pay them a lot more. This has been true, not just about AI, it's been true for a long time. So I think a lot of us have thought about how we can have that more of a revolving door and pipelining and preparing people for industry, but then they come back. And a lot of people in our space like to be at research computing, even if they're not making what they could make in industry, because the environment is great. They get to do creative things, and it's not overly managed. I mean, I am the director. I could tell people what to do, but then they go tell me what to do. So it's like, I mean, it's a university, right? So, but the environment's very nice. But I mean, it's hard to compete. So, on the hiring side, that's one, the workforce piece. I think, though, that so many people are starting to get into AI already down in the elementary school levels now, that by the time they come out and the technology changes, they're going to be used to that change. So I think that's a bottleneck now. I think that it'll get better. I do think it'll get better.
Makes sense. Thanks. Any more questions, folks?
Yeah, we have 5 minutes or so left. So if you have any questions, please.
It's your last chance.
People can always reach out to me anytime. I'm happy to chat. There's probably a lot of questions that I didn't get to, a lot of topics that people have on their minds that may not have been covered here, and I'm happy to talk about them. I'm really, really happy that I got the invitation to speak to the group, and I will hopefully be able to interact with some of you going forward.
Well, we'll certainly keep in mind that you guys are working on something very serious and important, and keep it on the radar, and we'd be happy to see you again to share your new findings and new information with us in the future. Thank you.
Thanks, everyone.
Thank you, Bill.
Thank you.
Thanks so much, guys. Have a good weekend.